So again, let me just repeat, welcome to ASEG's webinar series. It's an ongoing thing that we've been having. This very likely will be the last one of the year for all of ASEG. It's actually hosted by Western Australia, and I'm the local chapter president there, Todd Majeski. But the talk is from Nadrah, Noor, Sazali, who's going to give us a talk on efficient exploration in the Bonaparte Basin using unstructured data analytics with ElasticDocs, which should be pretty interesting. It's going to be all about AI, machine learning, and how to save yourself a lot of time and effort. But first, what we'll have to do is, first things first, I'd like to thank our corporate members. So we've got, without these people, we wouldn't be giving this seminar right now. So I'd like to thank Corporate Plus, High Size, Total Seismic, Bell Size, and corporate also, Southern Geoscience, Santos, Transparent Earth Geophysics, and Doug. Besides them, you've also got a lot of brand sponsors. See, I'm not going to, even for WA, I'm not going to go through them because we just don't have time. But I really do thank them. They are very helpful. These are, again, the people that are helping support us across Australia. Now, since this is a Zoom talk, what we are doing here in ASEG is we make sure that we've got a bit of Zoom etiquette going on here. So if you do have a question or a comment, click down, just go down below and you'll see this little screen pop up, and just click on the Q&A and type in your question, and then we'll try to get them. We'll probably get to all of them at the end of the talk. Right. There are some upcoming webinars, but they are next year. These are the ones I know about. There's one on the 2nd of February and one on the 16th of February. And both of them will be, find out what the talks are about. So we'll wait and see on those, but they'll be coming up faster than you think. Right, and with that, let me discuss what we have in terms of member benefits here. Yes, we have a really nice technical journal, like Exploration Geophysics, where we've got research and case studies, not necessarily just from Australia, so it's quite a good coverage of all things geophysics. And we have our preview, a bi-monthly rag, which goes through a lot of what we're doing across Australia, but also with some good technical papers, which you probably have been getting that in the mail yourselves pretty regularly now. And yes, we have a reduced entry to the AGC conferences and free entry to the what used to be regular technical events in your state. So that's with the COVID, that's changed quite a bit, but it's still there. Job advertisements are posted on our website, and we do have a very good annual wine offer, which just passed. Hopefully people have taken advantage of that. And we do have social events in our states, and because things are doing so much better with COVID, they've opened up. So tomorrow, for instance, in WA, we're going to have our 50th anniversary AGM Christmas party at a brew pub. So hey, we're lucky because we're COVID free. And okay, but back to, it's definitely something that is a professional networking environment. So that's another reason to join, of course. And we do a fair amount of research funding and travel scholarships for students, including here in WA. What I do like is we offer free membership for students. That's kind of unusual and half price for retirees and recent grads. But the free membership for students means that anyone, if you know anybody that's interested in geophysics, just ask them to join. We'll let them in, and they can see things like this. They can network, etc. Pretty important. And so, how we do that, we have monthly email newsletters. We have our own website. We're on Facebook. We're on Twitter, along with a few other people like Trump. We're on LinkedIn. And what I think is really cool is we have our own little YouTube site in which most of these kind of geophysics talks are placed after the fact, and anyone without a password is allowed to view them. And so if you're interested in maybe trying to review something yourself, now's the chance. So with all that, it's pretty good. But let me get back to now our what happened there. I was a bad boy. Get back to my last slide, and let me introduce Ayin. So Ayin Nadrah Noor Sazali, she's with Iraya Energies, and she's a digital earth scientist in Iraya Energies. With her diverse background of domain expertise, geology and petrophysics, and also in data science, she designs and deploys innovative machine learning and artificial intelligence solutions for unstructured data using ElasticDocs to support geoscientists and engineers in their decision-making processes. She holds a master's in petroleum geology, bachelor's in industrial and computational mathematics, and a diploma in science physics. So with that, I'm going to just stop talking and stop sharing my screen, and I will pass the baton over to the talk that we're going to have.
Hello everyone, my name is Ain. I am a digital earth scientist for Iraya Energies. Our focus today will be to understand the geology and the risk associated to Bonaparte Basin in Australia. Data used for the presentation is exclusively using unstructured data ingested in Iraya's knowledge container ElasticDocs using the latest machine learning and artificial intelligence technologies. In this case study, I will walk you through on some potential problems or time-consuming tasks related to unstructured data containing reports, images, and presentations that you might face during your exploration or development stages. I will then provide you some recommendations and examples of how ElasticDocs can provide an aid to those problems by providing you an analytical tool for better and faster decision making. Before I begin, let's just go through a little bit of Bonaparte Basin background. For the exploration history, the exploration itself begins in late 1940s. It was regional work, but the focus was mainly on the onshore area. So the first well drill was onshore, which was in 1959, where it is called Spirit Hill 1, located in the south of the basin, followed by Bonaparte 1 well close to it in 1963, and then soon they started to drill offshore wells in 1967, which are Ashmore Reef 1 and Sahul Shoals 1. Where is Bonaparte Basin located? The image on the left shows the Australian continent. The Bonaparte Basin is basically located northwest of the continental margin. It joins with Mani Shoal Basin in the northeast and Browse Basin in the southwest. There's also Timor Trough that defines the northern boundary. The size of the basin is approximately 270,000 kilometers squared. It contains Mesozoic and Cenozoic sedimentary field in the northern part, whereas more than 15 kilometer thickness of Paleozoic, Mesozoic, and Cenozoic in the southern part. If you take a look on the right image as we zoom in, it appears that the basin consists of 14 structural elements as listed below. It is also reported that the most dominant feature in Bonaparte is number 4, which is the Petrel Subbasin, where it has up to 17 kilometers of Paleozoic to Cenozoic sedimentary field preserved. How does Bonaparte Basin develop? There are two periods of deposition. The initial period occurs from late Devonian to early Carboniferous, which is associated with remnant of a rift system controlled by numerous northwesterly oriented normal faults. The second period occurs during Upper Carboniferous to Younger Sedimentary, which draped the earlier rift blocks and leapt onto Proterozoic rocks, forming the flanking shelves. So there's no faulting in this later part of the succession. Another thing that is important to know in order to understand the Bonaparte Basin background is, of course, the petroleum system. In this slide, we have a summary for each element compiled from hundreds of well reports. The elements compiled consist of reservoir, seal, source, and trap. The reservoirs can be within Cretaceous down to Carboniferous period, and so does the seal. As for the source rock, both oil and gas-prone source rock are present. Can be from Cretaceous down to even deeper formations such as Cambrian source rock. The trap may consist of faulted anticlines, horst. There's also some stratigraphic trap such as delta sand and salt diaper associated structures. This map is basically just to show you the 12 acreage which was released this year. Outlined in red represents the block boundary. So basically this case study will be focusing more on the wells close to this location of interest. Up to this point, I hope you have gotten the gist of Bonaparte Basin. Now, in this case study, bear in mind, all the materials are based only on the unstructured data that we have ingested into ElasticDocs. When I say unstructured data, it means the text reports. It can be in Word documents or PDF formats, and also the images such as map, stratigraphic chart, theme sections, and so on. Based on ElasticDocs dashboard, there are currently 440 wells available in our database. The oldest well, as I mentioned before, is the first well onshore, which is called Spirit Hill 1. The youngest well available in our database is Barossa 6, which was drilled in 2017. The shallowest well is Nadrah, whereas the deepest well available is Escalon 1. Our ElasticDocs database currently have ingested almost 300,000 processes pages and 250,000 extracted images of Bonaparte Basin data. In this slide, this is a summary of play-based exploration pyramid in the oil and gas industry. We need to focus on the basin and play more than we focus on the prospect. On the right, in Iraya, we have customized this workflow using machine learning or artificial intelligence technology. It's basically to show you before having a location to drill. Given sufficient data, you would normally have a model to choose location from. But before constructing the model, you would already have some seismic or log interpretation. But before interpreting anything, of course, you would need to have some data to do the interpretation on. But in order to do that, you have to know which data to collect. You have to understand the regional background first, know the previous issues and lessons learned, also able to identify anomalies that might give a potential problems. These are the information or tasks that will take a lot of your time. Hence, this is where ElasticDocs comes in for you to crunch and ingest vast amount of unstructured data which contains previous experience exploring the basin. Our motto is to save geoscientists and engineers everywhere in search for new energy. On the left, you can see on the goals that you would like to achieve. We maybe want to increase your chance of drilling successful well, reduce unforeseen issues, reduce costs associated to unstructured data, or maybe more time for analysis so that you can bring more values in your studies. You can actually increase your chances towards that by letting ElasticDocs do the hard work. Let ElasticDocs transform all your unstructured data to structured data. Let ElasticDocs create map, correlate information, and classify information for you. Let our hero save you from being stuck underneath those pile of data to a clear space and mind which enables you to focus on what matters more. Less searching, more thinking. This is how we work smart. Hey, you don't have to take our word for it. We'll show you. Now, where to begin? Imagine yourself as a detective. As a detective, where do you start your investigation? At the crime scene, at the place where the problem occurs. So I guess in this case, one of your problems would be identifying dry wells, if there's any. From ElasticDocs dashboard alone, we figured out that there are 210 out of 440 wells were concluded as dry. That's almost 50% of the wells drilled in Bonaparte Basin are dry. And of course, your detective curiosity starts kicking and you want to know why are they dry. Using ElasticDocs search feature, seal and trap issues are identified as being the main reason for dry wells. Here are some extraction from several well reports to show you why these wells are dry. For example, in Bodacious 1A, it says here that the Titonian sand objectives was likely to penetrate outside of closure. Chrome well 1 says that there is no hydrocarbon accumulation in this well was due to the lack of effective top seal. This had actually caused them a total loss of approximately $8 million. Crane 1 claimed that the well may have been drilled outside of closure as well, which cost them $5.6 million. Endeavor 1 negates the likelihood of there being any structural closure present. There's also abundance of T-light presence, which reduces the ability to act as seal for Kuyipi Reservoir, and this had cost them a total loss of $7.9 million. P-Wheat 1 tells that there is a seal, but its continuity in the prospect area cannot be verified. So $8 million per well doesn't seem much, but remember we have 210 wells, assuming each well costs about 8 million. We have about 1.7 billion losses in this basin. And this includes only the cost associated of drilling operations and not on seismic acquisition or studies costs. However, think of it in the positive note, billions of dollars has been invested by others in data acquisition, and that we have the leverage and the opportunity to utilize all of them to increase chance of success in the next well. In any study, we would normally start with background research. Then we start collecting data. Once we have enough data, we analyze them and eventually make decisions. Usually the background research and collecting data are very time consuming, and we wish to focus more on our time and energy in data analysis and decision making instead. In our case, ElasticDocs is our solution. Below here, we have identified some common potential issues encountered at the beginning of geological study. The first one is the discrepancies in formation tops within the same area. We always need to ensure formation tops to be standardized to avoid confusion and complication during interpretation later. Second potential issue is limited understanding lithology distribution. It is important to identify anomalies across basin to avoid misinterpretation later on. For example, a false positive AVO response in salt area. The third potential issue is limited mineral composition understanding. We know that some cemented clay minerals and quartz overgrowth may affect the quality of reservoir, so not knowing this info can lead to a bad decision in determining parameters during formation evaluation. The fourth one is fluid distribution. Of course, it is always important to understand the fluid pattern to avoid drilling dry well. And the fifth one is pressure and temperature patterns, where we also need to identify overpressure anomalies and temperature trend. So all of these potential issues are actually related to regional understanding. From now onwards, I will show you how ElasticDocs can assist us in tackling these potential issues using only unstructured data. Let's start investigating the formation tops available. Okay, where to begin? Do you want to open each report one by one? Do you want to find information by skimming through page by page? Yeah, I don't want to do that either. So in ElasticDocs, what we can do, we could just start off by clicking on Image tab, where it has already classified all the images extracted from all reports. It seems that ElasticDocs also have classified some images into stratigraphic chart, so we can identify and assess all these images quickly. Once you can assess all the charts easily, you can start compiling them according to your needs or however method you want to analyze it. So over here we have some stratigraphic chart from Great Owl 1 well, followed by Bodacious 1A up to Barossa 1 sidetrack 1 well. After performing a well correlation from southwest to northeast and then start analyzing, we try to capture any discrepancies of formation naming. And it turns out there is. When you look closely at the late Jurassic level, you'll notice that there's some discrepancies in formation naming in Great Owl 1 and Bodacious 1A wells compared to the rest. It appears that both wells are actually located in Vulcan sub-basin, which you will see better in next slide, while the rest are not. Some namings found in the two wells are Upper Vulcan Formation, Titonian Formation, and Lower Vulcan Formation, which may or may not correlate to Flamingo, Frigate, and Ilang Formation in other wells. When overlaying the two wells, Great Owl 1 well and Bodacious 1A, on the structural elements map over here, the two wells are indeed located within the Vulcan sub-basin. Based on the cross-section image below, the Vulcan formation in late Jurassic, which is colored in red, only occurs thicker in the middle of the basin and disappears towards the flank. So when we look at Great Owl 1 well, it only penetrates Upper Vulcan formation, which may indicate that the well is located closer to the flank, whereas Bodacious 1A may have been drilled even closer to the center of the basin as it penetrates all three formations, which are Upper Vulcan, Titonian Formation, and Lower Vulcan Formation. Similar to stratigraphic chart, we can also compare table containing formation tops which are automatically classified as such in ElasticDocs. The formation that are only available in Vulcan sub-basin are marked in blue box. And then next, we've also compared the formation tops with general Bonaparte Basin stratigraphic chart as our reference, which was modified in 2011. And from our observation, we see that there are still a lot of discrepancies and additional formation names which we have circled in red. An example from Buffalo 8 well, we can see that Flamingo formation, which has used in this table, may be equivalent to the Clea formation, which we see in the stratigraphic chart reference that we are using right now. These discrepancies may become problematic if it's not handled from the beginning. Therefore, it is important to relook on the correlation to standardize back the formation naming across the basin to avoid confusion in the future. For the second potential issue is the limited understanding of lithology distribution. We know it is important to understand the lithology occurrence within the area before performing interpretation. Why? It's because some anomalies observed in log, for example, may not be due to the data spike or error, but actually due to lithology itself. For example, in Cache 1 well, anhydrite, coal, and even volcanic materials are observed, and each lithology actually gives different responses, like sudden high density log response or a very low density log response, and also sometimes slightly higher resistivity with low density response, which might be mistaken as hydrocarbon bearing sand. Now, in ElasticDocs, there's a feature called Lithology Cloud, which basically is a summary of lithology extracted from reports of each wells and provide you an overview of the distribution of phases in the well. You can pick several wells, extract the lithology cloud from each well, and compile them. From there, we try to analyze and come up with an observation summary. This is how the lithology clouds look like. We have several lithology clouds extracted from several wells here. The cloud basically shows the number of lithology being mentioned in all reports in each wells. Let's see an example in Barossa 1. You can see that sandstone is being mentioned the most, followed by claystone. I guess from there we can safely assume that clastic environment is important in this well. I can see that there's also mention of dolomite and anhydrite, which may have been found in cuttings or cores. So basically, This slide is just to show you an example on how we can utilize the lithology cloud in our analysis. For example, some wells have been selected from southwest to northeast area, and then from the lithology cloud we can have a quick summary and say that dolomites are being mentioned in almost all the wells selected, which is marked in red. This may also mean that dolomite may occur everywhere across the basin. And then there's also minor volcanic and anhydrite, which occurs in the well located in the northeast, and also some at the southwest, and it seems to be localized. In terms of whether we are in clastic or carbonate environment, the heat feature in ElasticDocs actually helps in showing the distribution of sand and carbonate across the basin. It turns out when I search for sand or carbonate, both lithology actually occurs everywhere. This can be supported by the stratigraphic chart over here, where carbonate environment occurs in the younger formation from Cretaceous to Neogen period, whereas the clastic environment occurs in the older formation from Triassic to Cretaceous. Here's another way of presenting the lithological data, which is across the formation. From the left, you can see a stratigraphic chart. This is to show you where the sandstone, the claystone, and the limestone are in which formation. And as we go to the right, we can see a tabulated information of additional lithologies such as dolomite, anhydrite, coal, and volcanic. Now, let's summarize this table together. We can see that dolomite occurs from Jurassic to Younger formation. Anhydrite and coal mostly occurs at the shallower formations, whereas volcanic materials only occurs from Jurassic to deeper formation. Simple! Now you have understood the lithology distribution across Bonaparte area and also by formation. Regarding on the occurrence of anhydrite, Cache 1 well observed anhydrite in cutting samples due to salt diapir occurrence at the area as shown in the tectonic elements map on the right. There's also some traces or minor anhydrite in Barossa 1 and Caltilda 1 wells in the northeast area, which may also indicate that a possibility of salt diapir nearby. However, no map is found for now. In this case, a new updated map is recommended to pinpoint all the location of salt to avoid some misinterpretation later on. The third potential issue is limited mineral composition understanding. Why is it important to understand it? It's because the reservoir quality prediction depends on porosity and permeability, and generally the porosity loss is mainly caused by diagenetic process, including mechanical compaction, quartz and K-feldspar overgrowth, carbonate cementing, and clay mineralization. Second, it helps to calculate matrix density more precisely during petrophysical evaluation. So similar to the image for stratigraphic chart, we can also assess the thin section image quickly from the image tab in the ElasticDocs. Similar to the previous lithology distribution, in this slide, for the mineral composition, some wells were selected and then the images and description of minerals are compiled and labeled on map. Based on the observation, we can say that overall quartz overgrowth and kaolinite is quite common in this basin. Mica is observed at the northeastern well, which is also supported by the lithology cloud. Highly corroded skeletal feldspar has been extensively dissolved, which forms secondary porosity is observed in the well in the south. Some patchy siderite is also observed in the southern well location as well. Intergranular porosity may be filled by quartz overgrowth, kaolinite, pyrite, and carbonate cement. There's also another way to correlate the images from different reports and different wells. In ElasticDocs, there's this one feature called intuition, which enables us to go deep dive on finding similar properties based on image. regardless on the distance or location of the image taken. So basically, these images with similar features are clustered closely to each other, as shown in the picture here. In this feature, ElasticDocs has already classified images based on map, stratigraphic chart, seismic, core, and thin sections. So if you want to have a more detailed classification, such as maybe grain size or mineral counts, that fits more on your investigation or study purpose, we can provide API link to access raw data and allows you as a user to perform your own image processing. The fourth potential issue is understanding the fluid distribution. Of course, it's not as straightforward, and there's a lot of aspects that needs to be looked at, such as pressure gradient, indication from cuttings and logs, before creating a proper fluid distribution map. What we have here is a good kickoff point to understand or see the patterns where the fluids are. For example, in this slide, I have searched on million scf per day, which should be indicating gas production if it's mentioned in the report. The search result is in the form of heat map, where we can see that the green color here are the wells that do mention the keywords. Then the hotter the color is, the higher the number of times such keywords have been mentioned in that area. From the map, we can see that there's a high density result observed in the northeast well, where we have Barossa 1 well, which was flowed about 30 million scf per day during the SD2. There's also other nearby wells, such as Evan Shoals 1 and Caldita 1 well, where the wells were also tested as gas. Similarly, barrel per day can be used to represent oil producer. So, as you can see from the map, high density result is observed in the western area. I guess we can say that most of the high producer are located here, which seems to be within the Vulcan sub-basin area. Up to this point, we have seen and understood the lithology, mineral, and fluid distribution across Bonaparte Basin. Let's apply the same lithology and mineral analysis into pressure and temperature distribution, except this time, instead of looking at the images, we are looking at plots. This slide shows an example of pressure distribution over plover formation. We can see the highest pressure observed is in the northeast area, where the pressure can reach more than 5,000 psi. Lower pressure trend is observed as we go down towards southwest area. From this pressure plot collected, an interesting thing to observe is that there are different fluid contact in different wells in the northeast within the same formation. For example, in Barossa 1 sidetrack 1, the gas water contact is observed at 4,100 meter TVDSS, whereas the gas water contact in Caldita 1 well is shallower, which is approximately 3,800 meter TVDSS. This shows some indication of possible complex structural and also different fluid system which needs to be further investigated. Apart from pressure, we can also look at the temperature distribution. It is observed that some localized area has high geothermal gradient. In some wells, thermal gradient may change by depth. It's either increasing or decreasing. An example can be observed from well Vesta 1, where the thermal gradient changes as the well goes deeper. Further investigation for Vesta 1 well, by comparing temperature and pressure side by side, it is observed that there is a significant increase in geothermal gradient when pore pressure increase. It can be concluded that the increase in geothermal gradient may be attributed to the effect of geopressuring in the lower part of the lower Vulcan formation. For the sake of finding hydrocarbon, based on the stratigraphic chart available on the left here, we can observe that production mostly occurs in Triassic, Jurassic, and Cretaceous. Most of the production are within Jurassic formation, where the lithology shows mostly sandstone, claystone, some dolomite, and some volcanic texture. There are quite a number of minerals that may be the culprit of poor reservoir quality in some area, but based on the reservoir quality observed from some of the wells, it shows that the quality within this formation seems to be fair to good. Now, to summarize, we know that regional understanding is critical and time consuming, as it involves dealing with very large unstructured data. Therefore, within a project time frame, if the time spent at the basin focus stage can be reduced with the help of our hero, ElasticDocs, more time can be utilized to focus on other stages. With more time available, explorationists will be able to take this opportunity to bring more value in their study. As we have gone through each potential problems that I have listed at the beginning, you may have seen an overview of the Bonaparte Basin and have understood how some things or some elements like lithology, minerals, pressures are distributed across the basin. Based on a quick look and putting some pieces of information together, we can see that most production are coming from Jurassic and Triassic, which with observed net pay of 18 to 60 meter thick, porosity about 11 to 29%, and 11 to 55% of water saturation. Given ElasticDocs analytics tools, such in-depth analysis can be performed in a couple of days, looking at 100 plus of wells, 10,000 plus of images, and 100,000 of pages. Overall, we estimated that such machine learning workflow using ElasticDocs is significantly faster and more accurate than the traditional workflows, which is reading reports well by well, creating my own maps just to know where the well locations are, extract and compile informations. So, 58 years of exploration history in 2 weeks? Sounds impossible? Not anymore. ElasticDocs save geoscientists and engineers everywhere in search for new energy. Thank you.
Well, thank you very much. That was a great talk, very interesting. And hopefully we've really got people thinking about the Bonaparte Basin, among other things too. So let's see, let's make sure, Ayin, make sure that you're on and ready to answer any questions by turning your mic on too. All right.
Hello, everyone.
Yeah. So we've got one question right off the bat, which is, what search term did you use to get results related to dry wells and get the well summaries that you presented?
Okay, thank you, Pat. So basically, the dry wells that were identified, it was identified from our dashboard module, which actually has been tagged to one of the metadata, which is the post-drill result metadata. So basically, from that metadata, we already know that the wells are, whether it's oil well, gas well, or dry well. So what I did is I just filter on the dry wells and then pick randomly on the wells. And once I view the report, there's a search tag where I could type in, I use the word dry hole just to verify that the well is indeed dry. And then to know the reason and get the snapshots, I basically mostly search in the geological summary, or of course the conclusion itself. So yeah, that's how I did it.
Sounds good. For me, I've got a question. So what different formats did you have in the wells? I mean, did you have from these wells? I mean, I would assume that you would have paper, PDFs, doc, Word files, et cetera, et cetera. What formats did you, I guess, did you input to your program?
That's true. Basically, just what you said. All the unstructured data format, which can be in PDF, can be in Word document, it can even be in Excel or PowerPoint. So basically, yeah, all the unstructured data format, it can be ingested into the ElasticDoc.
Okay. Sounds good. Yeah, yeah. That's what really I think can save a lot of energy by having this stuff be read into your system. I guess the amount of time it takes, a lot of it might be just taking all these different volumes and getting it into the system first. Pretty neat. Now, we've got a few more questions already popped up, so let's go see. It said, how much can a study like the one that you just presented cost if you were doing that yourself, I guess? Or maybe you
Thank you so much. Oh, okay. So yeah, thank you so much for the compliment. So basically, the study, the cost is basically would be I will leave it to my sales director on the cost part. But for the study that I did itself, because it's more on the ingestion part that we provide as a service. But the study that I did is basically I just use all the material that's already ingested and then just compile all the information into that package that you just have sent. So if you wanted to know on the course itself, you can contact me afterwards and I could connect you to our sales director. I'd be glad to.
Sounds good. Let's see. Now you've got, this is Bonaparte Basin that you've done. I think there's been some kind of overview studies by some of the universities here and stuff like that. So it'd be pretty neat to get together with these people, by the way, and kind of compare notes, if you will, or whatever. But this is quite fascinating. So it took you 2 weeks to basically go through all the garbage, if you will, and winnow out these facts. Pretty cool. Okay. Let's see. Now, for me, what?
Yeah, that's true.
Well, I've got a question. So, what computer set did you use? Are you using a rack of data, GPUs, single processors? What did you use as the computer hardware for this task?
As in for me to get this information.
So the data goes in, and then you've got your software package running. So what is that running on? What machine were you running it on? What kind of machine?
I'm just using a normal computer. It's basically the ElasticDoc itself. You just need a browser and then the credentials. So
oh no, I meant
okay. So for me itself, I'm just using a browser.
Mm-hmm.
For the ingestion. This one, yes, we are using GPUs, and also we have a partnership with Azure, Microsoft Azure, for storage in the cloud. And if you wanted to know even further, I think Ines would probably join in the chat and answer it for you.
Right. Okay, but yeah, so it's
Does that answer your question?
I think so. Yeah, in other words, that's essentially kind of always curious, how much compute power does it take to do something like this? That's kind of the questions. You know, it's taking some GPUs to crunch through this stuff and things like that. And another question maybe, let's see if we've got any more. We've got some more.
Yeah, I think Ines is able to take the question for further in the chat room.
Right. So let's see. So right now, one of your colleagues has said that he can work with any cloud provider, and it's a cloud-based solution is what someone else there is more relaxed. So yeah, quite interesting. And this does look like the wave of the future, right? Pretty much. And definitely, I think people are curious as to how much a study like this would cost them. So you can probably what they can do is if they've got your email, which we can provide, then they can contact you guys directly and go for that. And for me, definitely, I would think that this is just as functional for, say, a minerals mining type analyses, because if someone's trying to go in and kind of high grade, low grade areas and things like that, they've got a lot of reports that they'd have to go through. So if they could get something that pops it pretty quickly, then that's pretty good. There's another good question. This looks, in terms of age, environment, and minerals identification, do you reinterpret the data or just honor what the legacy data says? That's a good question.
Let me just. Okay, for the study, we don't reinterpret. We have the traceability of the data. So we honor the legacy of data, and then we could also actually trace back what have been done and what have not yet been done. So it's easy for us to not repeat the same work, the same study, or repeat the same mistake. So yes.
Well, and I think also
that's why basically
right. You did, for instance, try to decide whether or not formations are non-unique, and and so you're trying to say that perhaps this formation actually, with this name in this area, might very well be equivalent to a formation over there that has been renamed. So you are doing some interpretation, and I would think that you probably, if there's something that's very much anomalous, at least that'd be automatically flagged, like in one well or something like that when we're talking interpretation. So yeah, I think there's good possibilities of at least doing some kind of reinterpretation by at least flagging odd things and things like that in these studies.
Sure. That's basically where the geoscientist comes in to look back and then understand and then make it forward to interpret it later. So yeah.
It's pretty neat. Okay. And I think then, well, I think we've got almost all the questions that have come up here so far. We'll give it a few more seconds, but definitely you did get a thank you, awesome, excellent presentation, very impressive, and et cetera, et cetera. So that's always
Thank nice. You.
But yeah, it was, I find this quite fascinating.
Yes.
And yeah, what's pretty neat is pretty soon we won't need processors or interpreters anymore. A little bit scary in the oil industry, but that's the way things are going. Just good programmers and good cloud.
Not exactly. We still need the interpreter. The interpreter is important. So even though the machine, we still need a human touch in it to QC it, to check it, and then later on, the one who does the thinking, the creative thinking, is the geoscientist, the human ourselves. So it's not purely on machine.
Not yet.
So this machine is an assistant for you to work, to reduce your speed. To reduce your time and then increase your speed to do the work. Yep. And more critical thinking.
Yeah.
Don't worry.
No, yeah, all joking aside, what you've done, as someone did say, you just don't need to do the boring stuff. And that's pretty much what I would agree to. It's a way to cut through a lot of the things that you would have to just grind through, and it's a lot more difficult for this thing to make a mistake if you're tired out. It's possible. Now, one last question from me. So now you did the study for this talk, and so how long did it take you then to decide? So once you had the information, you decide really what's important, what's not, and put it together. So you're going to make basically a report, which you've done. That's this PowerPoint is like an overview of a report. So how long did that take you after the computers were done with their work? As it, so you're an interpreter getting that.
I'm sorry. Okay.
Well,
do you mean once the computer have ingested the data?
Right, and then you've got all this information, and now you've made a report, this PowerPoint, for instance,
Okay.
your own report for this. So
right,
your own personal. I'm just comparing how much. So it's 2 weeks of the computer, and you working together to make an interpretation, and then you're done. Now you have to make a PowerPoint, or maybe to give your boss if someone wants to use this. I'm just more curious. Compare the time it takes to make one of these reports versus the one you've generated with the computer. The final output where you say, let's drill here and not here, versus getting the information. I'm thinking they're about the same amount of time.
So basically the study, well, that depends because it still needs some discussion with others. So, but then what I did to compile the data, it took me a couple of days. It took me about 2 weeks to get the information. But then of course, how depends on how detailed you want it to go. So depends on the discussion with the team as well. But definitely your time will be reduced a lot using the leverage that we have now.
Yeah.
The machine learning technology. So yeah.
All right. Well, I think let's look one more time, but I think that's it for the Q&A. So I think I'd just like to thank you again for the talk, and for people, thanks for listening in, and we'll let you go and relax, and we'll say until next time. All right, thanks a lot, and we'll shut things down here, I think.
Thank you, Todd, for the questions and everything. All right.
Okay, bye now. Bye everyone else.